Okay, in the previous 3 videos on molecular substances, I've laid the groundwork for intermolecular forces or intermolecular bonds. These are going to be the attractive forces that exist between molecules. And relative to that, there are going to be 4 basic categories of these kinds of forces. All right, there are going to be what we call the hydrogen bonds. There are going to be what we call the dipoles. There are going to be what we call the London dispersion. And fourth, we will also have what's called the ion dipole. Now, for the purpose of these videos, these 4 types of forces of attraction between molecules are not listed in an order of priority. Simply, they're listed in the order in which I'm going to deal with them. So the first type that we're going to talk about is the hydrogen bond. All right, and so we'll make a series of notes here. This is what we call a specialized dipole. So A number 1, any molecule that's going to be a hydrogen bonder is going to be also what we call a structural dipole. In other words, it's going to have opposite charges on opposite ends of the molecule. All right. Now, more specifically, this is going to be a molecule that contains an O, an oxygen, or a nitrogen, or a fluorine, where a hydrogen is covalently bonded to the O, the N, or the F. Note that all 3 of these atoms have high electronegativity. On the periodic table, remember, electronegativity increases left to right across the table. And as we go across the table, we shift from nitrogen to oxygen. So we go from N to O to F on the periodic table, where En is increasing. All right, so En, electronegativity, increasing in this direction. So fluorine is actually the most electronegative atom on the table. And remember, electronegativity has to do with the force of attraction of electrons that are in a bond between this atom and whatever atom is bonded to it. Now let's look at a specific example of each one of these. So in the case of oxygen, I'm going to use, again, for my model system will once again be water. And we see, by definition, we have an O in the molecule, we have an H in the molecule, which is covalently bonded to the oxygen. So we have an electronegativity difference. All right, we also have a structural dipole. We have a top and we have a bottom. This is arbitrarily defined. I could have flipped it around the other way if I wanted. that places opposite charges on opposite ends of the molecule. This line here just differentiates top from bottom. All right. And the adjacent, so if we had another water molecule present, that molecule can line up like this. Okay, placing its partial charges adjacent to the other water molecule. All right, and the net result is you're going to have what we call an intermolecular force or an intermolecular bond. Keep in mind that these are weak by comparison to a covalent bond or to a metallic bond or to an ionic bond. These are weak. All right, now what about some other examples? So let's take a quick look at another model, ammonia. And we can draw its loose formula this way. All right, it's a pyramidal molecule. Notice we have a nitrogen covalently attached to the hydrogen. And there is a top and a bottom to the molecule, just like with water. This end of the molecule is going to have a slight negative charge. This end of the molecule will have a slight positive charge. Top and a bottom. All right, I'll put my bottom over here. We can have another nitrogen or another ammonia molecule line up right here. It's going to have its little negative like that. And the net result is another intermolecular bond. So this is my IB or IF, as it were. Whatever makes you happy on that. As long as you understand it's the force of attraction between two molecules. All right, we can also look at a fluorine example. So here's HF. F being the most electronegative atom in the table in a covalent interaction with hydrogen. So again, we're going to have a little positive charge here and a negative charge here. Okay, there also is essentially a top and a bottom here, but we're going to do it sideways. Just flipped it over sideways. And if we have another water molecule adjacent, excuse me, I can't believe I just said that. If we have another HF molecule adjacent, all right, I'll put it here. We'll have our opposite charges. So a little negative over on this side, positive here, and our intermolecular force or bond, I'll use 3 dots to indicate it, is going to be right here. So this is my IB or my IF. Okay, again, notice that the bond is between the molecules, all right? So I think these 3 examples illustrate very well the hydrogen bond. Remember that for a molecule to be a hydrogen bonder, you need the presence of oxygen, nitrogen, or a fluorine, but in combination with that, you need a hydrogen which is covalently bonded to that particular atom in order to qualify. And then the bond is happening between the hydrogen on one molecule and the adjacent unshared pair of electrons on the oxygen or the nitrogen or the F on the adjacent molecule.